You've driven past it 100 times. A fenced-off yard on the edge of town, or tucked between two neighborhoods, full of gray steel boxes, ceramic insulators stacked like vertebrae, and thick wires running between structures to nowhere you can see. It hums. Sometimes it buzzes. And almost nobody who passes it could tell you what it actually does. That yard is a substation, and it is one of the most important nodes on the entire electric grid. Every bit of power that reaches your house passes through one. And the strange thing is, it's quietly doing two completely different jobs at the exact same time. Jobs so different you'd normally expect two separate buildings for them. By the end of this, you'll be able to look through that fence and read the whole thing like a map. Start with the problem the substation exists to solve. The grid has to move power over long distances, from a power plant that might be 100 miles away, all the way to your street. And to move a lot of power a long way without wasting most of it as heat in the wire, the grid uses very high voltage. We're talking hundreds of thousands of volts on the big long-haul transmission lines, the ones on those enormous steel lattice towers marching across the countryside. High voltage is fantastic for shipping power far, but it is completely useless for actually using power. You cannot run 345,000 volts into a neighborhood. It would need gigantic clearances, it would arc across anything nearby, and nothing in your house could touch it and survive. So there's a fundamental mismatch. The grid moves power at a voltage that's great for transport and lethal for delivery. Something has to bridge that gap. Something has to take the high transport voltage and bring it down, in stages, to the modest voltage that can safely run down your street and into your home. That something is the substation. Think of the transmission grid as an interstate highway moving traffic at enormous speed, and your street as a quiet residential road. The substation is the interchange, the off-ramp where the interstate slows down and becomes something a neighborhood can actually use. So that's job one, changing the voltage. And it's the first thing you can actually pick out through the fence. The biggest objects in the yard, those giant gray tanks, often with rows of radiator fins on the sides and a steady low hum coming off them, are power transformers. This is where the hum comes from. A transformer's whole job is voltage. It takes the high transmission voltage in on one side and hands out a lower voltage on the other. A line might arrive at the substation at 138,000 volts, and the transformer steps it down to something like 13,800 distribution voltage, the level that goes out on the poles or the underground cables running down your street. The fins on the sides are radiators, and the tank is full of oil, not for lubrication, but for cooling and insulation. Moving that much power generates real heat, and the oil carries it out to the fins where the air can take it away. That's why a substation hums, and why, on a hot day, you might hear the cooling fans kick on. So the first half of the substation is simple to state. Even if the machine is enormous, it's a staged step down, taking the voltage from highway level to neighborhood level. But if all a substation did was change voltage, it could be a much simpler place. The other half is where it gets interesting. Because a substation is also the grid's circuit breaker panel, the same idea as the breaker box in your basement, scaled up to the size of a parking lot. Look at all those horizontal bars and the wires connecting everything together. The central piece is the bus bar, a shared metal conductor that every incoming line and every transformer connects to. Picture a power strip for the grid. Instead of one line feeding one transformer feeding one street, the bus bar is a common junction where several lines and several transformers all tie together, so power can be routed from any source to any destination. If one line goes down, the bus bar lets the substation feed your neighborhood from a different one. Connected to that bus bar are the circuit breakers. These are the heroes of the yard. When a fault happens, a tree falls across a line, lightning strikes, a squirrel bridges a gap, the current doesn't politely rise. It explodes, sometimes to tens of thousands of amps in a fraction of a second, enough to melt metal and start fires. A circuit breaker is a switch built to interrupt that, to force open a connection carrying that monstrous current and snuff out the arc that tries to follow. all in a few hundredths of a second. And then there are the disconnect switches, the ones you can actually see open, swinging a metal arm up into the air. Those aren't for faults. They're for people. They physically isolate a piece of equipment so a crew can be certain it's dead before they touch it. When a line faults, the breaker opens and isolates just that one section, and the rest of the grid stays lit. Which raises the obvious question. A circuit breaker is just a switch. How does it know to open in a few thousandths of a second, in the middle of the night, with nobody standing there? It doesn't. The breaker decides nothing. The decisions are made by protective relays, and they're the part of the substation you can't really see, because they live in that small building at the edge of the yard, the control house. A relay is a device that watches. Every line coming into the substation has sensors on it measuring the current and the voltage, continuously, thousands of times a second. In normal operation, the numbers sit in a familiar range, and the relays do nothing at all. But the instant a fault hits, the instant the current spikes to that impossible level, the relay recognizes the signature and, in milliseconds, sends the command, "Open this specific breaker now." This is the real intelligence of the grid, and it's why a single tree limb doesn't take out a whole city. The relays are set up to trip the smallest possible section, to open just the one breaker that isolates the fault and nothing more. See the problem? Pick the tightest boundary around it, cut it out, leave everything else running. All automatically, all in the time it takes you to blink, all without a person on site. So now you can walk the whole thing. A transmission line arrives at the yard from a plant far away, at high voltage. It passes through a disconnect switch and a circuit breaker, its on-ramp and its safety valve, and lands on the bus bar, the common junction. From the bus bar it feeds into a power transformer, which steps the voltage down to distribution level. And it leaves the far side of that transformer on the feeders, the lines that run out of the substation and down your street, to the small can-shaped transformer on the pole outside your house, which steps it down one last time to the 120 and 240 volts your outlets use. That's the substation. It is the single point where the transmission grid becomes the distribution grid, where the highway becomes your street. It's the one place the grid can change its voltage, reroute its power, and protect itself from its own faults, all in the same fenced yard. And there are tens of thousands of them across the country, almost every one of them unmanned, sitting quietly, doing all of this on its own. The humming gray boxes change the voltage. The bars and breakers route and protect the power. The little building things. 3 jobs, 1 yard, no people. So the next time you drive past that fenced-off lot of steel and insulators, you'll know exactly what you're looking at. The interchange where the interstate of the grid slows down to become the road you live on, protecting itself thousands of times a day without a single person on site. But here's the tension the whole thing quietly rests on. Every bit of that protection depends on the relays being able to see a fault, and the way they see it is that sudden, violent spike in current when something goes wrong. That spike doesn't come from nowhere. It comes from the heavy spinning machines inside conventional power plants, which dump a huge surge of current into a fault the instant it appears. That surge is the signal. As the grid fills up with solar panels and batteries, which connect through electronics that barely produce that surge at all, the spike is getting smaller. The fault is still there, but the flag it used to wave is fading, and a substation can only protect what it can still see.